tank which contained water started to leak from a hole in its base. The volume in the tank 24 minutes after the leak was 4 meters cubed. The volume of water in the tank 60 minutes after the leak was 2.8 meters cubed. The volume of water in the tank t minutes after the leak started can be described by a linear model between V and T. Find an equation linking V and T. So a linear model, so that's y equals mx plus c. Or in this case, it's going to be V equals mt plus c. I know it's going to be that way round because V is the dependent variable. The volume depends on how much time has passed. Right, so I want to know what the gradient of my line is going to be and what the y-intercept is going to be. Well, let's look at the information we're given in the question. I know that when t is 24, v is 4. So when t is 24, that's like the equivalent of my x. Remember, t is my independent variable. So that's like my x. When t is 24, v is 4. When t is 60, v is 2.8. So my gradient then, m, will be the change in v divided by the change in t. Which gives 1 over 30, or minus 1 over 30. So v equals minus 1 over 30 t plus something. I can now substitute either of these coordinates in. I'll substitute in, I'm going to substitute this bottom one in because I can see that the minus 1 over 30 times the 60 will be nice and simple. You can pick, it's up to you. Either of these will work perfectly well. So 2.8 equals minus 1 over 30 times 60 plus c. So the minus 1 over 30 times 60 will just be minus 2 plus c. So c is 4.8. And therefore my linear model will be v equals minus 1 over 30t plus 4.8. That is my linear model for explaining how the volume of water depends on the time that has passed. We now need to use this model to find the initial volume of water in the tank. Well, initial means t equals 0 at the beginning. So if t equals 0, if I substitute 0 in here, then I find that v would just be minus 1 over 30 times 0, so that's just going to be 0, plus the 4.8, which will be 4.8. So the initial volume of water in the tank is 4.8 meters cubed. Part II, we need to find the time taken for the tank to empty. Or tank to empty, that means that V equals 0. So if I make V 0 in my model here, and rearrange and solve this equation, times both sides by 30, so 4.8 times 30, I get 144 minutes. So that is the time taken for the volume to become 0, the time taken for the tank to empty. Part C. Suggest the reason why this linear model may not be suitable. Not be suitable. Well, we only need to give one reason here. Well, this model seems to suggest that the volume is going to be going down by a constant amount each time. Each minute that passes, the volume decreases by -1/30. And that's probably unlikely. The volume is unlikely to go down by the same amount, by a constant amount, each minute. For example, as the water pressure changes, as less water is in the tank, you'd expect the rate of change of the volume to be different. So you could say, for part C, you could say, unlikely that the volume will change by the same amount each minute. That's one thing you could say here. Alternatively, we've seen that when, alternatively, let's use a different colour. We've seen that when t equals 144, v is 0. If you try anything bigger than 144, if you substituted 145 into this equation, then you would find that v would actually be negative, which obviously doesn't make any sense. You can't have negative volume. So this model is not suitable for any value of t above 144. So you could make some sort of comment about that. There are other things you could say, but I think those are probably the two most common things you could say are problems with this linear model.